Hi everyone, I'm Akram from Team 1, and my teammates are Brandon, Dari, and Nada. Our topic is monocular depth estimation, which is the challenge of converting the image or video from a single color camera into a mapping of the depth at every point. Essentially, we want to convert this to this. It is a grayscale representation of a depth map, where darker pixels show areas that are closer to the camera. Different color schemes can also be used to display the same information. So why does any of this matter? Well, depth estimation is a very important tool that provides access to three-dimensional spatial data of our surroundings, as opposed to a two-dimensional image. There are many use cases where it is necessary for a machine to have easy access to this information in order to better understand the world around it, whether it is a vision-guided robot assembling a product, an augmented reality system, or a self-driving vehicle. Many current solutions use bulky and expensive sensors that employ rotating laser rangefinders, also known as LiDAR, stereo cameras, or infrared dot projectors. These sensors perform actual depth measurements to some degree, but are not easily scalable and have issues with resolution and refresh rate. New developments in processor architecture design has led to the mass manufacturing of very cheap GPUs or tensor processing units that can perform rapid machine learning operations. So what if we can create a machine learning model to convert the color images from a camera module into a fairly accurate depth map? Well, that would save us a lot of space and money. But how do we design and train a model that can perform this task?
We are going to need a lot of data. We obtained our data from the Digital Image Media Lab from Yonsei University in South Korea. They provided RGB videos of various indoor and outdoor scenes with corresponding depth maps in the form of individual image frames. In order to keep data size down, we only used 5 scenes from the indoor section. Since frames that are close together tended to be almost identical, we only kept 1 in 5 frames, resulting in 6 frames extracted from the original video per second. Each image was paired up with its corresponding depth map, and all of the image pairs were then encoded into one single large binary file in order to improve loading performance. Since we wanted to avoid overlap between training, validation, and testing data, the dataset was split up accordingly, after which the individual sections' frames were shuffled. This process, however, yielded only 3,600 image pairs. We circumvented this issue by applying data augmentation to the training images. That way, every epoch will be different, and we'll have nearly unlimited data. The image pair was first randomly rotated, and then center cropped to remove the black edges. The resulting image was then further randomly cropped to yield a smaller portion of the image, and then a random horizontal flip was performed half the time. This means that many 224 by 224 pixel images can be extracted from a single original 480 pixel by 640 pixel image.
It's time to build a machine learning model that can convert color images into depth maps. A few architectures were tested, but many fell short of this difficult task. Traditional convolutional autoencoders were not able to restore any detail from the compressed feature maps in the middle layers. When adding skip connections such that each layer receives the previous 2 layers, some improvements were made, but GPU memory became a serious limitation. A fresh new conditional GAN-based approach was then attempted, where the generator was given an RGB image concatenated with noise and was then asked to produce a depth map. Its loss was determined by a traditional CNN classifier. This approach proved very difficult to train, however. We observed a breakthrough after stumbling on a paper that suggested adding skip connections between encoder and decoder layers. We used MobileNet v2 as our encoder and built a decoder using regular convolutions with interpolation upscaling. This model architecture allows less heavy processed features maps to have a greater impact on the final depth image. The result is that generated depth maps have much better clarity and structural detail. The skip connection module is what allows the feature maps to bypass convolutions. This module is implemented in the decoder and receives 2 inputs, the previous layer and a feature map from MobileNet v2 with twice the height and width of that previous layer. The former is upscaled by a factor of 2 in both dimensions in order to match the latter, after which they are both concatenated together into a combined feature map. This then undergoes 2 layers of convolutions and finally returns the output for the next block. The autoencoder employs 5 decoding steps, out of which 4 receive skip connections. In its forward pass, the model appends the output from each MobileNet v2 layer for a given RGB image into a features list, which is then indexed and passed into skip connection blocks. These blocks are chained together until the image is upscaled back into the original dimensions. 2 batch normalizations are also dispersed in between to smoothen the gradient descent.
As the famous saying goes, seeing is believing. And so, we put together a demonstration using a video of an incredibly cute dog to generate an incredibly not cute depth map. As you can see on the left, we have an owner trying to convince the dog to put its face in between her hands and failing miserably. On the right, we can see the depth map generated, with the background indicated in bright orange and the foreground indicated in dark purple.
The loss function we used is RMSE, or root mean squared error. Essentially, this loss function compares the generated depth map and the ground truth pixels by iterating over every coordinate and applying the equation shown. The final loss is quite close to an average depth difference between the two images. It is worth noting that the loss depends greatly on the range of possible depth values and so is not comparable with loss values from other datasets, unless depth normalization is done the same way. Our final model architecture achieved a training loss almost 3 times lower than the baseline model, and a 35% lower validation loss. It did also take 4 times longer to train, but both models trained very quickly compared to other CNN architectures. Here's a comparison of the baseline and final model on test samples. The baseline model is able to extract more structural elements from the color image, but fails miserably at accurately predicting depth, as it seems to rely too much on brightness for its prediction. On the other hand, the final model is a little bit blurry, but is able to accurately predict the depth of different areas in the image. Here's another set of samples that show input RGB, depth, ground truth, baseline model, and final model. One observation our team members made is that finding a suitable data source is very important, and a dataset should only be selected after a thorough examination of all available options. As choosing the NYU dataset initially led to the generation of inaccurate depth maps of RGB images due to the dataset containing significant noise and missing features. Further, our team noticed a major improvement in performance yielded by utilizing skip connections in an autoencoder coupled with transfer learning. The model with skip connections succeeded in extracting significantly more details when compared to our baseline model, comprising of simple convolutions, thus providing much higher quality depth mappings. It is also important to note the difficulty in applying monocular depth estimation machine learning model to a real-world application, despite our team experimenting extensively with a wide range of models, including autoencoders, GANs, CGANs, and skip connections. Our best model occasionally fails to accurately identify the depth of certain objects in settings where there is a large number of objects in the foreground. This may lead to potentially hazardous situations in a real-world applications, such as obstacle detection using depth estimation in self-driving vehicles. Thank you for watching. Now we're open for questions.